everybody, and welcome back to Linear Algebra with me. Today we're going to talk about orthogonal projections onto subspaces. And the reason we want to do this is we want to write our vectors in terms of an orthogonal basis. And like Gracie, we already have linear combinations. Like, we don't need that, right? Like, what do you mean? What if we're talking about a vector that isn't in the span of our basis, though? So you can't write it as a linear combination. Like, what can we do about it? That's where projections are going to come in. So real quick, let's recall from Calc 3, the projection of U onto V is given by this little formula here. And then you can alternatively write it this way because we know the length squared is just V dot V. I don't know, something about seeing the U dot V over the V dot V makes me happy on the inside. And I've always preferred that. So choose whichever one you like, whatever is easy to remember. And then you may have also heard the projection of U onto V being described as, like, let's say you have a little sun over here and he casts a shadow. The projection of U would be equal to that shadow that U has made on V. Okay. Another way to think of it is this is the part of U that is parallel to V. So we can call him U parallel. But then that's not all of U. Like, if U has like a parallel bit, how do we get back to U? Remember that by definition of projection, the vector connecting these two tips is perpendicular. So if we were to use vector addition, we could go along the projection. Okay, go along the projection and then line the tail of the other part up with the tip, and then we get back to V. And then we're going to just call that new part U per, like that. Okay, so we can express U as the part that's parallel to V and the part that's perpendicular. That's kind of cool. But notice, I want to point something out that's kind of interesting. I hadn't really thought about this before I had to explain it, actually. If V had been longer, then the projection of U wouldn't have changed. Like, we don't really care how far out V goes. The projection's not changing. The shadow stays exactly where he was. Like, so how can we describe the set of all the V's that are like going in that direction? Well, that's the span of V. So instead of just thinking about projecting U onto V, we could think of it as projecting onto anything, any scalar times V. So that would be the span. So we could say that U projects onto, we'll say, the span of this little V. And then we would denote that, denoted U parallel is equal to the projection of U onto, and we're going to use big V, not V the vector now. But let's keep thinking about this. So we've got V stretching all the way up this way, and now it's also going to stretch all the way that way because we're talking about the entire span. And the projection of U onto the entire span of V is now just like, in this diagram, it's about 2/3 of V. That would be in the span of V. That's totally in the span of V. So now the projection of U onto the subspace V is also in that subspace. That's pretty cool. Just made a huge leap. We were talking about projecting one vector onto another vector, and then I brought the word subspace out because we were talking about span. Can we do this for bigger subspaces? Like, can we go bigger than just V? We totally can. Let's introduce some terminology before we get into how we can do that. So if we have V as a subspace, we call x parallel the projection of x onto the subspace V, and we write it exactly like we did before, except this little v right here, he's not a vector anymore. Notice he has no vectorness on him. It's the big V, the subspace. Okay, but how do we calculate this x parallel now? We had a formula. That was the Calc 3 formula. Let's look at this theorem. So we've got x is a vector in Rn. We have V is a subspace in Rn, and our subspace has this nice orthogonal basis. We can then write x as two components, its parallel component and its perpendicular component, just like I talked about, where the parallel component would be in V and the perpendicular component would be in the orthogonal complement of V. Remember we talked about that? The orthogonal complement takes every vector and it's like, oh, is it perpendicular to everything in V? Yes? Well, and it goes. And so if we have x is parallel to V via the projection, then the only part that would be left over is this perpendicular part. Okay, so that's a bunch of like name stuff so far. Now, for the rest of this theorem, we've also got a way to calculate x parallel. And notice it's just we take the projection and we do it for the first element in the basis, all the way out to the last element of the basis. So the projection is just, well, how much does the basis contribute for V1? How much does this piece of the basis contribute? How much does this piece of the basis contribute? And I would like to point something out. Dot product means scalar. Length means scalar. Here is our vector. So this is a big fat scalar times a vector. So the projection ends up being a linear combination of the basis elements, and that's how it's related to what we've already been talking about. All right, and then we still haven't finished talking about the theorem. It's a long theorem. And then we can get x perpendicular by just taking x and subtracting off the parallel component, which we already know what x is, and we already know what x parallel is, so we don't really need an entire formula in order to find x perpendicular. Okay, so let's talk about this. Let's check. I don't really want to go into the proof. Hopefully you can see like, oh yeah, I can like kind of justify that to myself. But for this example, let's use this to check it because this is going to be pretty intuitive. So we've got the span of E1 and E2 in a subspace R3. So I've got my axes for R3 down. So E1 is going to look like this guy. And E2 looks like that guy. And so the span of those guys is like this plane right here. So that's our span. Notice he kind of looks like R2. We're going to put it in quotes though. So now we want to see what the projection of this x right here is onto that subspace. Well, if we were to take our x, he's like going to come here, and we project him down onto our space, then this guy here, it's really like, do you remember when we did linear transformations and we were like, the transformation that like removes the z component? That's basically all that's happened, because this is orthogonal right here. This is a right angle. So our x and y components live, but he's now been pushed down onto the xy plane and has no z component. So let's use our formula from the previous theorem to see if we do get what we think we should get, which is just x component, y component, no z component. Okay, so x parallel equals the projection x onto big V, which is going to be x dot E1 over the length of E1, which I told you, I like looking at these dot products. It makes me happy. So we're going to go ahead and write the magnitude as a dot product. Oops. There you go. Yes, I wrote that correctly. Okay, let's do x dot E1 first. So that would be like 2, 3, 2 dot 1, 0, 0. So hopefully you can say, oh, we would have 2 times 1 is 2, and then plus a 0 plus a 0. So it's just 2. So that's good. And then x dot E2, I'll go ahead and write that out as well. So that's going to be 0, 3, 0. There we go. Whoa. 0 plus 3 plus 0. There we go. Okay, so let's plug that into our equation. So x parallel is going to be equal to a 2 over, and then hopefully it's easy to see that E1 dot E1 is just going to be 1 times E1 plus 3 over 1 times E2. So that's going to be 2, 0, 0 plus 0, 3, 0 equals 2, 3, 0. And there you go. So it's x, but with no z component. This is exactly what we wanted to happen. So hopefully that means it's working correctly. Yes, it's working correctly. Okay. So let's do this again, but for something where we don't know the outcome walking into it. All right, so now we have V is the span of these two vectors here, and then we want to find the projection of X onto our subspace V as well as Y onto our subspace V. So we're going to do two different ones, same problem. All right, lots of dot products are about to be taken. Let's do projection of X onto V first. So that's going to be X dot V1, V1 dot V1, not equal, then V1 plus X dot V2, V2 dot V2, V2. Okay, so X dot V1, let's go ahead and find him first. So that's going to be -3 times 1, so -3. 1 times -2, -2, and then 0, 0. And then X dot V2, that's going to be -3, -4, so +12, and then 1 and 1. And then our zeros. And then we need to do our magnitudes for V1 and V2. So that's going to be 1 squared, -2 squared, -1 squared, 2 squared. That's 10. V2 dot V2. That's going to be 16, -4 squared, plus 1 squared, plus 0 squared, plus 3 squared. That's a 26. Okay, so then let's plug all these numbers in. So we have a fifth, or -5 over 10, V1, plus 13 over 26, V2. So that's a -1/2 and a +1/2 for our coefficients of V1, V2. All right, and then if we distribute those in, going to get a -1/2, +1, +1/2, -1. Okay. This is bugging me. There we go. And then plus, let me get our last vector. It's going to be negative half, negative 5 halves, negative 3 halves. No. Oh, that's y. That's not v2. I'm sorry. All right, v2. That's the negative 4 vector. Okay. So negative 2, positive half, 0, 3 halves. That's going to be equal to negative 5 halves, 3 halves, 1 half, 1 half. There we go. So that's our first result. And now we get to do this all again for y. Yay! Because once wasn't enough. Okay, so projection onto v, but for y now. That's going to be y dot v1, v1 dot v1 times v1. So thankfully, we get to reuse a little bit of what we already did because we already know these magnitudes of v1 and v2, which we'll use in the denominator. Okay, so let's go ahead. We'll calculate y dot v1 first. So that's going to be negative 1, 1, and then negative 5, negative 2, 3, negative 3, negative 1, 9, and 2, 18, and then that's gonna be 30. Then y dot v2. So negative 1, negative 4. So that's positive 4, negative 5, 1, 0, 27. That is 26. So let's plug those in. So we've got 30 over 10 v1 plus 26 over 26 v2. So pretty. It's just 3v1 plus v2. I love it. So let's think about that. I'm going to put my 3 here so I can visualize. So he needs to multiply and then add for our result over here. So that's going to be 3 minus 4, negative 1. And then that'll be 3 times negative 2, negative 6 plus 1. And then 3 times negative 1, negative 1. 3 times 2 is 6. Oops, I wrote a 1, but I meant 3. All right. Notice something very interesting. Remember, we call this y parallel, the part of y that is parallel to the projection. Y parallel was equal to just plain old y. Why would that happen? What explanation is there for this? Y was already in V. Y was in the subspace. So when you project something in the subspace to something in the subspace, or when you project something in the subspace to the subspace, it's just itself because it's already there. Okay. So that was kind of a cool example. So why are we so interested in these projections though? It's because the distance between the projection and the actual vector, these guys are the closest. So if you look everywhere on the subspace, that projection is going to be the closest you can get to the actual vector. In fact, so important, it's called the best approximation theorem. So if you have a subspace and we have a vector, then the projection, so the part that's parallel, is going to be the closest vector in V to X. So a bunch of confusing lingo right there. what you should think of is the distance between x and its projection is going to be less than the distance between x and every other vector in that entire subspace. You're like, you know what? That makes sense, because if we look at, like, here we go, here's some sort of random plane, and here's a vector, then his shadow that's down here, these tips are as close as they can possibly be. Some random vector v over here is not going to be closer. The closest you can get is straight down to that subspace. So that's what this theorem is trying to say. Okay, why do we care about this though? This allows us to approximate x by using x parallel. What I mean by that, for example, we'll say, how is this an approximation? Because that is the name of our theorem. So for example, if, I'm going to switch variables, if y is not a vector in our subspace V, then this equation, so we'll use the basis of V to make a matrix, like that. So let's say y is not in V. That means y is not a linear combination of these guys. So if he's not in there, this equation has no solution. Well, that's really boring. We don't like when things don't have solutions. So what if we think about, so what we know is that y parallel will be in V. So then instead of having y on the right-hand side of our equation, we're going to have y parallel. So y parallel can be expressed as a linear combination of those v's. We just saw it happen. We used projections and real quick, see? It's a linear combination. It's a linear combination of the basis vectors. So then this has a solution. This is useful. So if the distance between y and y parallel is like really small, this is useful. And hopefully, I think we're going to have time to get into this next week. It's called the least squares approximation. It's like, oh man, we don't have a solution, but golly, it's really close to being in there. What would its answer be if it was in there? And it's not something we have time to talk about right now. Hopefully we'll have time to talk about it next week, but for now, that's all I've got for you guys. So I'll see you next time.